Imagine looking up at the night sky, not just at the familiar pinpricks of light, but at the very fabric of the cosmos bending, warping, and reshaping reality itself. We often think of space as an empty void, a passive stage upon which celestial bodies play out their ancient dramas. But what if I told you that space itself is alive, dynamic, and capable of feats so profound they defy our everyday intuition? What if the most massive objects in the universe aren't just sitting in space, but are actively sculpting the light that travels across billions of light years to reach us? This is not science fiction. This is gravitational lensing, the universe's most astonishing optical illusion, a cosmic funhouse mirror that reveals the invisible and unlocks secrets we could never otherwise perceive. Prepare to have your perception of reality shattered as we delve into the mind-bending world where gravity itself becomes a lens, bending light and showing us the universe in ways we never thought possible. The story of gravitational lensing begins not with a telescope, but with a radical new idea about gravity. In the early 20th century, Albert Einstein revolutionized our understanding with his general theory of relativity. He proposed that gravity wasn't a force pulling objects together, but rather a consequence of mass and energy warping the very geometry of spacetime. Think of spacetime as a trampoline. Place a bowling ball on it, and it creates a dip. Roll a marble nearby, and its path curves towards the bowling ball, not because the ball is pulling it, but because the trampoline's surface is curved. Einstein's equations predicted that light, though massless, should follow these curves in space-time. Where massive objects like stars, galaxies, or clusters of galaxies reside, they create significant warps, bending the path of light that passes nearby. This phenomenon, predicted by Einstein in 1916, was a theoretical curiosity until it could be observed and confirmed. The first definitive confirmation came in 1919 during a total solar eclipse. Astronomers Sir Arthur Eddington led expeditions to observe the Sun's corona, and crucially, the apparent positions of stars near the Sun during the eclipse. If Einstein was right, the Sun's immense gravity would bend the starlight passing close to it. The stars near the Sun should appear to shift slightly from their usual positions. The observations, painstakingly measured from two different locations on Earth, matched Einstein's predictions with remarkable accuracy. Suddenly, the abstract concept of warped spacetime became a tangible, observable reality. This single observation catapulted Einstein to global fame and validated a theory that would fundamentally alter our view of the universe, paving the way for understanding phenomena far beyond the solar system, including the cosmic lensing we witness today. Gravitational lensing manifests in several fascinating ways, depending on the alignment of the source, the lens, and the observer. The simplest form is microlensing. This occurs when a star or planet passes in front of a more distant star. The gravity of the foreground object acts like a temporary magnifying glass, briefly brightening the background star. This technique is invaluable for detecting exoplanets, even small ones, as their gravitational pull can cause subtle but detectable variations in the lensing effect. Then there's strong lensing, the most visually dramatic. When a massive galaxy or galaxy cluster lies directly between us and a distant background galaxy, the light from the background object can be significantly distorted. We might see multiple images of the same galaxy, or even arcs and rings of light, famously known as Einstein rings, formed when the source, lens, and observer are perfectly aligned. The most common manifestation of strong lensing is the appearance of multiple images. Imagine looking at a distant quasar behind a massive galaxy. Instead of seeing one quasar, you might see 2, 3, or even 4 distinct images of the same quasar. appearing at different points around the lensing galaxy. This happens because the light rays from the quasar take slightly different paths through the warped spacetime around the foreground galaxy, all converging on our telescopes. These multiple images are not separate objects. They are echoes of the same distant source, refracted by the immense gravity of the intervening mass. Studying the positions and brightness of these multiple images allows astronomers to precisely map the distribution of mass in the lensing galaxy, including the elusive dark matter. Perhaps the most profound application of strong lensing is its role in mapping dark matter. We know that the visible matter, stars, gas, dust, only accounts for a fraction of the total mass in the universe. The rest is invisible, detected only by its gravitational influence. Gravitational lensing provides a powerful tool to see this dark matter. When light from a distant galaxy is lensed by a foreground galaxy cluster, the distortion pattern is dictated by the total mass present, both visible and dark. By analyzing the subtle stretching and shearing of background galaxy images, astronomers can create detailed maps of where the dark matter is concentrated within the cluster. These maps reveal that dark matter forms vast, invisible halos around galaxies and clusters, providing the gravitational scaffolding upon which visible structures form and evolve. Weak lensing is subtler, affecting the shapes of millions of background galaxies across the sky in a more statistical way. Instead of dramatic distortions like Einstein rings, weak lensing causes slight, random elongations and shears in the shapes of distant galaxies. While the distortion from any single foreground object is tiny, when astronomers analyze the shapes of vast numbers of background galaxies in a particular region of the sky, they can detect a coherent, collective shear. This collective shear reveals the presence and distribution of intervening mass, predominantly dark matter, on large scales. This technique is crucial for cosmology, allowing us to study the large-scale structure of the universe, how it has evolved over billions of years, and to place constraints on cosmological parameters like the density of dark matter and dark energy. Beyond mapping dark matter and studying cosmic structure, gravitational lensing is an indispensable tool for measuring cosmic distances and the expansion rate of the universe. When we observe multiple images of a single variable object, like a quasar or a supernova, that is lensed by a massive foreground object, the light from each image travels a slightly different path. If the source object varies in brightness, we can observe the same light curve repeated in each image, but with a time delay. This time delay depends on the path lengths and the gravitational potential of the lensing mass. By accurately measuring these time delays and understanding the mass distribution of the lens, astronomers can calculate the distances to the source and the lens independently. This provides a standard ruler, or standard clock, in the cosmos, independent of traditional distance measurement methods, allowing us to refine our understanding of the Hubble constant, the rate at which the universe is expanding. Gravitational lensing is not just a scientific curiosity. It's a fundamental tool that is reshaping our understanding of the cosmos. From revealing the distribution of invisible dark matter to providing independent measurements of cosmic expansion, it acts as a natural telescope, magnifying and distorting light in ways that unlock profound insights. As our observational capabilities improve with instruments like the James Webb Space Telescope and future generations of ground-based observatories, the power of gravitational lensing will only grow. We are only beginning to scratch the surface of what these cosmic mirages can teach us about the universe's structure, its evolution, and the fundamental laws that govern its existence. The universe, it seems, is constantly playing tricks on our eyes, and we are learning to see through the illusion to the profound truths hidden within.